Hi and welcome to the video lecture series on thin film flow modeling and simulation in the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work at the Division of Machine Elements here at Luleå University of Technology. Now this is the third part of the fourth video lecture on the application of finite difference method, and here we will devote the attention to the force balance and clearance relation, and then also on some numerical issues that one may encounter when solving the Reynolds equation. The sources of literature in this topic are many, and I've chosen only to list the course compendium section 5.6, which is exactly on the discretization of the Reynolds equation by means of the finite difference method. But for the interested reader, I've also chosen to list the book Multi-Level Methods in Lubrication, which also involves quite a lot of detail and important such on the discretization. Next up, discretization of force balance and then some numerical. So when it comes to the force balance and clearance relation, we have already seen and discussed that the actual clearance is nothing that we normally know. And here we have expressed in discrete vectorized form the gap between the surfaces h here in bold upright font. So ht, the clearance, is just a scalar. Alpha is the inclination of that wedge-shaped bearing, and L the length of it, and X is the vector holding all the discrete nodes xi. Normally we know the bearing load, and the simplest way of posing the force balance in discretized form would be to say that the discrete integral of the pressure, which is just this plane sum, should equal the applied load. But we can write this in more condensed form, just as a scalar product or a product between a row and a column vector like this. And when we do, we are now trying to find the clearance ht that actually makes the absolute value of f minus delta x times the dot product between this one vector and p less than a certain tolerance. And it turns out that the relationship, this can be found by studying the dimensionless equation for the force balance for the load carrying capacity. So if we just integrate the pressure and make that expression dimensionless, then we will clearly see that in this case the response in terms of f would be proportional to 1 over ht squared. And if we now view the solution procedure to find that ht that actually makes the pressure satisfy the force balance, it would look like this numerically. We start with some initial guess and we solve the system, we get the P, the pressure, and then we check if this absolute value, if the force balance is satisfied. That means that this absolute value is smaller than a tolerance. Typically it's not, and therefore we need to somehow update the clearance HT, and we insert it into the Reynolds equation, which means that we now have a new determining matrix, and we solve it for a new pressure. Hopefully we check the tolerance, and well, at least after some iterations of this, if it goes in the right direction, we will find the clearance that actually makes the pressure satisfy the force balance condition here, and then we're done. Finally, there are quite a few numerical traps and issues involved with solving hydrodynamic lubrication problems, and even more if we consider elasto-hydrodynamic lubrication problems. Let's just have some order of magnitude here for the different terms. So we know that the film thickness is typically of micrometer order. Perhaps in a large thrust bearing in a hydropower, for example, it may be 50 and perhaps even up to 100 micrometer large film thickness. But still, when we cube this, we get the epsilon value to be the cube of that relatively large 100 micrometer value. It will still be quite small, and if it were only 1 micrometer, it would be very, very small. And the pressure then, when we solve this equation, would be of the order of megapascals, and the term in the right hand side, the C, which we differentiate, would be, as you know, in proportion to the film thickness, at least if for the incompressible case, where the density does not appear, but the density variation is rather small, and therefore the C term wouldn't be that much varying anyway. So what we see is they are very different, and one main conclusion we can draw is that epsilon is extremely small, and this may lead to truncation errors, and they can be quite large. One solution to this, one remedy to this, would be to non-dimensionalize the problem and use scaling parameters that actually scales these variables to be of reasonable order in relation to each other. And this is and the scaling we have considered before for making the problem dimensionless is such. So it's possible, but it's important to actually not only for having fewer numerical solutions, but also for the numerical errors to make the problem dimensionless. And with this, I end this finite difference method part of the video lecture series on thin film flow modeling and simulation. And we'll see you in the next part, which will be about wear.